So with this last part here, we're going to talk about how do we measure it and then how do we quantify the absorption. Now that we've kind of gone into the processes, we've talked about the chemistry, the things like that, how do we actually measure it? And we've kind of talked a little bit about these different measurements, but now we're going to go a little bit more deeper dive into the system here, into this. So absorption measurements. So the influence of absorption on any given solute and soil combination is often determined experimentally. So we can use other systems. So like if I did an experiment with glacial clays from Illinois on a contaminant, well, we can use those in order to estimate for my system. But we have to actually do this for, usually you can't, the different soils that are in there will influence the different chemicals. So sometimes we have to find papers that relate to that. So there's really two ways that we can do this into our system. We can do batch tests, which I've talked about, batch tests, and we can also do column experiments. Now, you could do this in the field, but generally they don't let you dump contaminants into into an area and watch it happen. That's why Borden site, Cape Cod site, some of these other places around the world are very famous, is because it's some of the places that we're actually able to dump contaminants into the ground and actually watch them under natural systems versus doing a column experiment or a batch experiment here. So the batch experiments, most common because they're very easy. You have a test tube here. You got your soil, you got your water, you mix it up, and the samples are mixed, and it goes over things. So these are really referred to, and we've kind of already talked about this, is what we call absorption isotherms. So this is what you'll refer to them as absorption isotherm. Batch experiments are absorption isotherms. ISO, same temperature, so these things are all done at the same temperature because of the system in here. And with the absorption isotherms, you get the concentration in the solution, C, and then this is the mass of the solute absorbed to the solid per unit mass of soil, And I kind of showed this before, and then we get the line, and then we get KD this way. We can also do column experiments where we have a column. We pump into the column of soil here a known concentration, and then we see how much comes out. We know how much we put in. We know how much we're getting out of the system. One of the things that we usually do is we pump them in through the bottom and watch them come out the top. This way, if there's any air that's trapped inside of the system inside of here, the air gets pushed out. If you go the other direction, you can sometimes get air pushed into there. So generally, we do these columns where up is on the bottom part of the thing. So if we're taking this from a system, but we usually just put whatever soil we have from our system inside of our little columns into here. And then we look at our breakthrough curves. We look at our reactive and our non-reactive, and so this is our, and so this could be time in here, and so we can look at the differences between the two breakthrough curves, and we've already kind of talked about this and stuff like that. And so we can model these things, and so these are the kind of things that we can do. The problem with these are really quick and fast and easy to do, and I've done lots of these with different types of contaminants, especially new emerging contaminants or new things. We need to have these for all the different soils so we can make modeling predictions of the system. These, because you can only put one concentration into the soil and then you have to set up a whole bunch of them, you can get this. Column experiments are also referred to as permeameters, so you can do permeameter tests inside of them, and you put a head on here and you get, you can change the head so you can simulate maybe deeper down inside of a system inside of there. And so we look at breakthrough curves with these. So both of these methods have problems with kinetics and distinguishing between absorption and other reactions. So basically they kind of just, that's why we lump it all together. And so these can take, and if we could do field experiments, but again, they won't let us do that, which is just silly. They should let us dump, highly toxic chemicals into the, okay, there we go. Okay. So how do we actually analyze this and come up with this KD, and then how does this fit into our advection dispersion equation, which is really all you guys really care about, right? Yay, yay, equations. Oh, well, maybe not, but That's what we're going to say in the system here. Okay, so for linear absorption, isotherm models, okay? So for cases where absorption is fast and reversible, so that it's coming down there, it's sticking and it's moving into the system and stuff like that. This is what we've shown before with our system here. We get our data and we get our KD, which is in length over kilograms, or liters over kilograms and stuff like that. And so this was our concentrations and things. Notice it has to hit 0, 0. So note that the interpretation passes through the origin, because if you don't have any contaminant in there, you can't have any absorbent onto it. So we always fit the data through the origin in these particular systems. And so when we do these things, this is our negative control. We control it. We get our KD, which is our slope of our system. If the experimental data can be fit to a straight line passing through the origin, this is called a linear absorption. So if it's a straight line and it passes through the origin, then it is linear absorption. And we're going to get into some other ones where you get to, we'll get into Langmuir and some other ones in just a second here. And so the concentration of the mass of the solute absorbed to the solids per unit mass of our kilograms here, so this is in milligrams per kilogram, equals our KD times our C, which is our concentration of the solute under equilibrium conditions, and this has got units in milligrams per liter, and so where KD is our distribution coefficient. I think we've had some papers where we looked at KD. Most solutes and soils combinations fit this model, okay, especially at low concentrations. So at low concentrations, we can figure out the KD, and a lot of times you'll see those inside of papers and stuff in there. So the advection dispersion equation with linear absorption, I can show you that. Hold on one second. So I just wrote it up because we've written this up quite a few times. So the advection dispersion equation with linear absorption into here. So here's our advection dispersion equation that we've seen before. If we substitute in here our equation up here for linear absorption, since we know what our linear absorption is over here, and so we substitute in our KD over zinc, and we rearrange the equation, we get this. And then if we go inside of here, and this right here is our retardation factor, or bulk density divided by the porosity, or the amount of saturation, and since this is a saturated system, times the porosity of the system, times our KD, which is what we determined here experimentally, goes into our retardation factor. And so when we rearrange the whole equation, we end up with this. So this is our advection, the advection dispersion equation with linear absorption. This is how we usually look at it in here. RF, we can use either capital R or RF. You'll see it both ways inside of the literature, so I just wanted to make sure I point this out here, where RF is greater than 1. If it's equal to 1, then that falls out of the system, and then we have like a salt. And then we have just our advection dispersion equation inside of here. So that's our and remember our retardation factor is equals to small rf if you'd like to, and that is the advective groundwater velocity over the average velocity of the retarded system. So when we look at comparing those two, we come up with the retardation factor, and we can plug that in here, and then we can look at the change in concentration with time, and then we can look at this equation. And so this is where we can start adding in and showing that as we increase this retardation factor, then you can think about, like, if I'm increasing this number here, what's that going to do to the concentration with time? And so those are the kind of things that you do with modeling of these particular systems. So if we have a groundwater flow velocity and we look at the unretarded, so a lot of times when we do these experiments, we'll compare them to a salt that is put into something, or if we could use the actual water molecules itself. So sometimes we'll use the stable isotopes of water, and so we can actually trace the water systems, and then we can compare that to the thing. And so we can see that in the system we will get a retardation factor. We compare our breakthrough curves into the system. And so this is all based upon it being linear. Now, I want to go a little bit into what happens when we have nonlinear. And this also happens with a lot of speciations too, especially when we get into higher concentration. What we'll have is what is nonlinear, and how do we deal with that? Equilibrium sorption models. So how do we deal with things that maybe aren't linear? So what happens inside of these systems here is, again, we've got our things here. So this is our concentration in the solution, and this is our sorbed onto it with the mass and everything that I've said before. Okay, so what you can have here is you can have one system where it does this. So up to a certain point, under a low concentration, you can have that KD value, but once you hit a certain concentration of the solute, you can't get any more sorbed onto it. And so this is referred to as a single site, or we usually refer to these as Langmuir, after the man who developed the equations for this, so Langmuir. This is a Langmuir type of a thing inside of there. Now you can also get multiple sites, so you can get it having a absorption like that, and then something like that, and then finally going into there where you'll have multiple site. This is also referred to as Langmuir. It's just multiple site. It was also developed by Langmuir inside of there. And again, under certain low concentrations, and then you'll see that it levels off, and then finally it'll go into there. And then the last type is kind of exponential type. And so this is the exponential type sorption. And this is referred to as Freundlich. So this is the Freundlich type of thing, where you have it exponentially growing. You don't have these different sites that happen inside of there. So sorption tests do not always fit this linear model. So sometimes they fit a multi-site, sometimes they fit an exponential. So we've already talked about the Langmuir, and we already talked about the KD in here. So what happens with this Freundlich here? So the Freundlich type of sorption, like isotherms, this is when it becomes into equilibrium. When we do those batch tests or the sorption test, it has to be coming into equilibrium. It's like if, so you change the concentration in the solute to get these systems inside of here. So our concentration inside of over here, absorption equals Kc to the n power, which is the exponential function. So this n here is, note, if n equals 1, then it's linear. But you get this exponential look over in here, and so you're going to get an exponential here. So on a log C versus log C star plot, you can determine the K and the N from that, because then you can substitute them into there, because then this will become linear under a log-log graph. This will become linear, and then you can determine your K and your N off of that. And so retardation factors for a Freundlich, so we're going to look at retardation factor for a Freundlich type of isotherm will be RFF, so the retardation factor Freundlich equals 1 plus the bulk density of the soil, K, and Cn minus 1 over the saturated concentration. Generally, N is less than 1 will result in a concave. So you can get a concave, and N greater than 1 is convex. Convex curve. I.e. sorption's ability to increase with concentration doesn't make sense. So we usually just see them getting concave inside of in the systems inside of here. And so this is the Freundlich isotherms. So that is Freundlich. So if we go back to Langmuir, we go into the multiple site and everything like that, there are ways to look at the two site, multiple ways of looking at it. So if you have two surfaces into there, if we have single sites and we have double sites into the system. So if we have the Langmuir, so it is Langmuir isotherm. Based on the assumption that the solid surface possesses a finite number of absorption sites, and that some types of solutes are preferentially absorbed to specific types of sites. Okay, so if you have a single site with the upper limit absorption, so that's C over C star equals 1 over alpha beta plus C over beta. So where alpha equals the absorption constant. So this is the binding energy. And beta equals the maximum amount of solute which can be absorbed. So this is the max amount absorbed. So this is in milligrams per kilogram. Now if you had a double site, C star over C, you can get alpha 1 over the first one plus the second site plus alpha 2C da da da, where this is the absorption constant for the first type, this is the second site, this is the maximum count of solute that can be absorbed to the type 1, this is the type 2, and all of these type of things can go into there. And if you have multiple beyond that, usually we only have 2, but sometimes there could be some that are in there. So for nonlinear absorption models, Freundlich and Langmuir, when incorporated into the advection dispersion equation, it makes it more difficult to solve, okay, especially analytically. We really would need, so numerical solutions are often used. So in many cases at low concentration, the data, especially if there are only a few points, can fit into any one of these 3 models. And so we usually try to pick the simplest. So what we're trying to say here is that even if you have a Freundlich type, it can kind of seem like it's linear here, which makes it so much easier to model and stuff like that. And so we usually try to simplify these things. But with computer modeling and with a lot of the more advanced models, they can take on these very analytical solutions into here and really put it into there. So I generally recommend that you use the simplest model. So if you're going to be dealing with low concentrations, which generally is inside of soil, I try to just stay with my nice simple absorption model. I really try to avoid going and extrapolating up into these upper systems if I can't. And you can also look these things up for literature and use the models that are already out there in order to do this. But generally I stay with these lower end ones.